that we were doing in class yesterday.
Okay.
The problem number 1 from the mock exam.
Okay.
So right now, we've already solved for lambda once, right? And now lambda is taking on a range of values, correct?
Correct.
Okay. But in our integral, lambda is supposed to be a constant, correct? Because dp
okay.
is our variable.
Sure. Let me share my screen here. So this is the handwritten solution I made. Okay. So yesterday when we were talking in the class, the first part of the, when I first explained it, what I did was to say this droplet diameter, ignore this part. This was the second thing. We just considered the droplet diameter to be 15 microns, fixed value. Yes, right?
Yes.
So in this place where you want to compute lambda, you just plug in 15 microns and you got that number 1.77. You remember?
Yes.
Okay. So you got that number and then you computed the probability for m equals 0, m equals 1, m equals 2, m equals 3, and so on and so forth.
Yep.
That part you get it. Then in this actual problem, the droplet diameter is not a single number. It follows a normal distribution, which has a mean and standard deviation. So we say, all right, the number of particles per droplet follows Poisson distribution with a lambda parameter. And that lambda itself scales with the droplet size. You make a larger droplet, lambda will be larger. You make a smaller droplet, it will be smaller. Right? So we leave, instead of plugging in a fixed value for the diameter, which I'm calling x here, I just leave it as a symbol saying x cube, making lambda itself a function of the diameter or x.
Okay.
Okay. So then when I write probability for having m particles, where m could be 0, 1, 2, 3, and so on, that probability depends on lambda, where lambda itself depends on x. Okay. So then that's why I wrote it out in my handwritten solution. The probability of m taking a certain value depends on the diameter x through lambda, because lambda depends on x. To get P of m for all possible values of the droplet diameter, we should consider the probability of x taking a certain value.
Right.
Right? So what we did was to say, if the probability of there being m droplets is this expression, where lambda depends on x itself, then the question becomes, what is the probability that x will take on values between, say, x and x plus dx? That is the definition for probability density function, which is f of x dx.
Okay.
Okay. So what you do is this f of x dx, I wrote here, this f of x dx is the probability that x will take a certain value. And this p of m is the function whose value you are trying to estimate for all possible values of x. So you set it up as the average value of p of m over all possible values of x is P of m that depends on x multiplied by x taking on a certain range of values and integrate over the range of all the values of x.
So what would be all the values of x? Would that be I guess what are the upper and lower bounds of that integral?
Right. So
is it the smallest diameter within the standard deviation and the largest diameter of standard deviation?
No.
Or is it 0 to infinity?
It is 0 to infinity because the droplet diameters can of course, diameter has to be a non-negative number. So it has to be 0 is the floor and infinity is the largest. Theoretically, both 0 and infinity doesn't really exist. It's only the mid values. And those mid values follow a certain distribution. In this case, I have told that that distribution follows normal distribution, or that distribution is normal. Okay. So what I would write here is for f of x, I would substitute the normal distribution, which has a standard deviation and a mean parameter. And then I need to integrate this expression from the smallest value 0 to the largest value infinity. Of course, if you plot this normal distribution, it will peak around the value of the mean, the central value, and it will become 0 at far away from the mean on either side. Like it will be 0 near x equal to 0. It will be 0 near x equal to infinity.
Okay.
So then once you set it up, this part is the probability of having m droplets, which depends on the droplet size itself. And then this part is the probability of x taking on a certain value with a mean and standard deviation. You set up this integral, and that's it. At this stage for this module, we just want to make sure you are able to set up such an integral. And evaluating this is maybe later in the course. There are numerical methods that you can apply because it's not easy to integrate such an expression. It's not something you can simply analytically integrate.
Okay, so the whole point of the exercise was to set up that integral, not necessarily integrate and solve for it.
Exactly. I've written it here. Understanding the probability of getting m particles averaged over all possible values of x is the goal. It is a calculation of the Poisson probability considering the fact that x can assume a range of values. That's it. Doing the actual calculation is not the goal. It's to understand what to calculate.
Gotcha. Okay. That makes sense.
Okay. So if I mean, okay, in theory, if this problem appears in the exam, if a student is able to reason their way up to here and say, I have the expression for P of M, I have the density function in here, and then I have the dx and the range of limit integration written down. That's it. No more questions. They have understood what needs to be computed. How is a totally different question? How is, like, you can always figure out a way, you can use a software, or there are ways to do this approximately.
All right. Thank you. I had another question regarding the secant method that we did in class. I think it was last Thursday.
Okay. Okay.
So
by the way, for the mock, I also posted the solution using secant method if you want to consult that. If you want to try solving that as well.
Let me take a look at that real quick, because I did end up doing the whole table up to 4 iterations. And I ended up getting some different numbers than what I wrote down in class.
The numbers can slightly depend on the initial guesses. It's not always that you will get the answer by 4th iteration for all the guesses. So if you do many iterations, you will eventually get the same answers, but it could take more or less iterations.
So I see on this example for the secant method, your first guess for xi minus 1 was 0.9, and the xi is 1,
Sure.
correct?
Yeah, you can pick different guesses, sure.
Okay. How are we sure about our guesses? Because like with the bisection method, what I did was I put the equation into the calculator,
Yeah.
and then I found the roots of said equation, and
Okay.
those were my guesses, right? So are we supposed to do the same thing for the secant method?
So in practice or in reality, you always have a calculator. So you may say that I will just solve it using my calculator and use almost the same number as my guess, so I can, get the steps. That's what people would do. Um, if you didn't have a calculator and you just are, or if you're not using the function in your calculator and you just want to do the method, what you would do is pick a guess, something just by starting. Let's say this is your function. I would pick something like, let's say I substitute 0. I would get what, 1 plus 1 2. So at f of 0 the function is 2. And then if I would pick another value, like the second guess, something that takes the function closer to 0, so that it's, even if it's not a perfect root, it's at least somewhere a root may exist. And then I'll go through the iterations and then find out that, let's say I converge to a certain value like 1.1416. The test of whether that is a real root or not, you just substitute back in the function and see if it gets you 0. If it doesn't get you 0, then maybe some calculation error is involved. So to
Hmm.
your question, there is no universal guidebook on how to select guesses. That's why you use the graphical method to see how the function looks like, and you pick some values where the function is closest to 0 or seems to cross 0, or two values between which the root is seen to exist. You can do something that you can try a few things and see what works. There is no like a rule on this is how you go about selecting it.
Okay. Yeah, so on the Excel sheet I just downloaded from Canvas that
Mm,
has the secant method in it, I
mm.
put in the guesses that we got from class, right?
Okay.
And I'm getting completely different values for
Which file? One or two?
2.
Okay, so you want to do secant, this one, secant method, right?
Yes.
So what guesses you had?
In class we had 0 for xi minus 1 and 0.2 for xi.
Okay, and is this agreeing with what you're getting?
Yes, from the Excel sheet. But when I did it by hand,
Hmm.
I got different answers.
Different answer meaning what's your answer from other calculation?
So for my calculations, the f of xi that I get is 1, and then the f of xi minus 1 is 1, and then the f of xi I get is 0.7613.
Okay, I don't need those. What I'm asking is, you said you got a different set of x values as the converged root, right? What is that?
Uh, I only did it to the fourth iteration,
Okay, at
but
4
it
iterations,
it
what did you have?
it for the fourth titration, I get 1.5631, which I know is not right because it's not converging to a value.
I mean, you should also think about, if this is, if you think this is a root, the first thing it should do is to satisfy the function. If you compute the function using this number, it should go to 0. If that doesn't happen, you know that it's not a root. Even if you have done many iterations, it doesn't matter. So if in the class, what did you say was the range of guess values I gave?
The range.
Like
the
the I minus 1 and I. What two guess values did I give?
0 and 0.2.
And this is what we are getting, 0.4396.
Yes, and that's
Okay,
what I'm
and then
getting using the Excel file.
okay, and then if I do 1 and 2, or 2 and 1, I'm getting 1.14. Okay, so there are two roots here. That is, if I give 2 and 1, I'm getting a root. If I give 0 and 0.2, I'm getting a separate root. And both of them seem to satisfy the function. So in this case, what we would do typically is to graph the function and see what exactly it looks like. Okay, so is this the graph of the function? Okay, so I'm going to have to create a graph just to visualize the function. And that's where graphical method really helps. It helps you at least see for these nonlinear equations. You can't even have a theory that says these are the number of roots you need to look for. Like if it's quadratic or a cubic or a fourth order, you know it has 2, 3, or 4 roots. But an equation like this can have an infinite number of roots, and nobody is asking you to calculate all of them. They're just asking you to calculate any one root of those, or a root in a certain interval or something.
Okay.
Okay. So when we say solve, it means find a solution, not the solutions or all the solutions.
Okay. All right. That clears things up a bit, I think.
Yeah.
All right. I have to go to a lab. I'll email you if I have any more questions.
Okay. Thank you.
Thank you, sir.
Yeah. Thank you. Bye.
Bye-bye.